So today we're going to see this result. What is the lower bound on sorting algorithms? What's the lower bound for the sorting problem itself? Right. Okay. So what do I mean by a lower bound? I mentioned earlier, let me just again tell you, lower bound for a problem means that I should not be able to solve it better than that particular time. If I say lower bound for sorting problem is omega uh, some fn, then it says that the sorting problem cannot be solved by any algorithm whose running time is better than that fn, right? Whatever that function may be. We'd like to see, we like to investigate what's the lower bound for the sorting problem. And it turns out that this lower bound for the sorting problem would be omega n log. That says what? That says that there does not exist any sorting algorithm that runs better than n log n time. Right here, although I'm saying there does not exist any sorting algorithm, but it actually means that there does not exist any comparison based sorting algorithm. Right? Now, what do I mean by this comparison based sorting? So, in this type of algorithms, so is it problematic? Hmm. So, let me just check how to turn this off. Okay, just trying to figure out how to turn this off. If you then enjoy. So, so is this okay now? So I've removed it from this main screen. Hmm? Okay, so let's come back to what we're discussing. Okay. Okay, so the lower bound for the sorting algorithm would be n log n. That means like it says like there does not exist any comparison based sorting algorithm that runs better than n log n time. Okay. Now, what do I mean by comparison based sorting? Like, comparison based sorting, for an example, the algorithms that you have seen so far, all of them are kind of are comparison based sorting algorithms, right? What are these uh, comparison based sorting? These are actually the algorithms where you need to compare the objects, right? So these algos compare two objects and based on the outcome of the comparison, the algo decides its next step. Right. So that's the comparison based those are the comparison based sorting algorithms. Right. And now what you have to the yes. So that's the those are the comparison based sorting algorithms. And this is the reason that I said if you recall the first class where I introduced this sorting problem. There I said the input is n objects from a well-ordered set. Right? And I can sort those objects. And this is the algorithms that we use for sorting those objects are basically the comparison based algorithms. Right? So, okay. So if I am to figure out a comparison based, this lower bound for the sorting problem says that if I am trying for a comparison based sorting algorithm, then so I'll please don't bother about this. I'm not still getting what's the problem with this. Are you able to follow what I'm saying? Okay. So then, so stop messaging, right? So, okay, yes, fine. So now what we're going to show that while solving the sorting problem, n log n is the best thing that we can hope for. Like when we're trying for comparison-based sorting algorithms, and we already know few algorithms that actually does sort in n log n time. For example, merge sort and quick sort in some cases as well. Right? Okay. So to prove this result, first you must know. So the result, let me write the result. Mm, There does not exist any comparison based sorting algorithm that correctly sorts an objects in better than n log n time. Okay, this is the result that I'm going to. Now, let me ask you, what could be a possible way to show such a strong result? So, if you pause a little bit and just appreciate this result, what we are saying, what we are saying here, we are not trying to figure out any kind of algorithm that runs better than n log n time. We're not just doing that. We are saying that suppose we tried that to sort n objects in, let's say, better than n log n time, and we failed. It might be possible that someone else can try to sort them in better time and they might succeed. But here we are saying something very strong. If we are not able to solve it, then no one can. Actually, this problem is not at all solvable in better than n log n time when we are going for comparison based sorting algorithms. Okay, so this is actually guaranteeing for all comparison based sorting algorithms, right? All of them should be taking at least n log n time. Okay, so this is some kind of a very strong result that we are saying. Okay, so how to deal with that? So we have to come with a new idea for this. Right? And the idea is of something called a decision tree. So what is a decision tree? So a decision tree, it's another way of looking at a comparison based algorithm. It's a more generic notion. It's not only, I'm saying this compare decision trees are not only for this sorting problem, it's for any kind of comparison based algorithms. You can, for any other problems also, you can think about a decision problem. You can think about this decision tree. Right. So what do you have here? So at each point, so we are going to track, we'll forget about all the other operations, just we'll focus on the comparisons that we'll be doing. Okay. So we'll just see that how many comparisons are we uh, going to perform in a particular algorithm. Okay. Okay. So as the name suggests, this could be some kind of a tree. So I hope you're familiar with the tree. So trees will be having some nodes, like some nodes will be internal nodes, some are, yes. So of course you'll have some root and leaf node, internal nodes. and there will be some edges along it, right? Okay, so it's that kind of structure. Right? So I am going to represent an algorithm in terms of a decision tree, right? So I'll write as, so for example, I'm taking an example of just sorting three numbers, A1, A2, A3, right? Okay. So I'm going to sort these three numbers. So, and what are we, what is the tool that I'm going to use for sorting these three numbers? Comparisons, right? So I'll compare two numbers. Comparison will always happen between two numbers, and I'll look at the outcome of one particular comparison, and then based on that, we'll decide what would be our next step. Right? That is the comparison based algorithms that I said. Right? Okay. So let's say I first compare A1 and A2. Okay. So this is a comparison. So its answer could be either yes, or its answer is could be a no. Okay. So now if I see that A1 is smaller than A2, let's for the time being, let's assume that all the numbers are distinct. Right. So let's say A1 is indeed smaller than A2. So I'll be in the left part. This answer is yes. So then I'll be comparing, let's say, I'll be comparing A1 with A3. Okay. This comparison app. Fine. And suppose again, so this answer could be yes or no. Right? Now, if I see that A1 less than A2, the result, so I'm asking whether A2 is less than A3 or not. Okay. So if yes, then can you tell me the sorted order? Yes, the sorted order would, I mean, the question is, if I see that the answer, uh, so first I have made this comparison, right? Whether A1 is less than A2 or not. So I see a yes. Someone tells me that A1 is actually less than A2, right? And then I at that point when I know this answer of this A1 less than A2 is yes, then I cannot decide what is the sorted order. Right? I have to do some other comparisons. Right? Now I do this comparison, let's say A2 less than A3. And again, I get a yes answer. Then at this point, I can tell what is the sorted order. And the sorted order would be A1, then A2, then A3. Right? So A1 is the smallest, then A2, then H. Right? Now suppose I at this point I see a no. So I know that A1 is smaller than A2. A1 is smaller than A2 because I have got yes here. But A3 is smaller than A2. Then can I tell what is the sorted order? At this point, can I tell what would be the sorted order? Is it A1, A3, A2? So far, if we have seen a yes here and a no here, what does that tell you? It tells that both A3 and A1 are smaller than A2. At this point, I know that the A2 is the maximum of all of these three, right? So I need to perform to get to a sorted order. I need to make one more query, right? And what would be that query? I have to compare A1 with A2. Is this clear? Now I'll again have two options. I could have yes, or I could have a no answer. Okay. So if I get a yes answer at this point, yes at this point, and so far up to this, I know that A2 is the maximum of these three numbers. Right? Now I have performed one more comparison and I have seen this. Oh, sorry. I have to compare with A1 with A3. Right? Okay. So now if I see a yes answer, then can you tell me what would be the correct order? Then I can say it's A1, A3, and then A2. Okay. And if I see a no at this point, so I can also tell what's the correct order. It will be A3. So A1 is less than A3. Its answer is no. So A3 is the smallest. Then comes A1 and then comes A2. Okay. Now we can do the similar thing in the other direction also. When I at the first comparison, the result is no. Right? So I see here A1 is less than A2. This query is having a no answer. That means A2 is smaller than, sorry, A2 is less than A1. Right? So I need to now compare what about this A1 and A3. So I need to compare now. So this information I know at this point. I need to now compare this question. I need to put this question. Okay. If I got a yes answer, then if I got a yes answer, that says what? A3 is more than A1. So at this point, I have got the correct sorted order. And what is that? It's A2, then A1, and then A3. And if I see a no here, then what would happen? I have to come. So no means what? A3 is smaller than A2. A3 is smaller than, sorry, A1. Okay? So at this point, I know that which one is the maximum. A1 is the maximum because A1 is more than both A2 and A3. And to decide the sorted order, I need to now compare A2 with A3. Right? And so again, I'll get two. There are two possibilities. One is yes. If A2 is smaller than A3, then I know what's the correct order there. It will be A2, A3, A1. And if it's the other way, the answer is the other way, then I know what's the correct order. It's A3, then A2, and then A1. Is this okay? So I'm looking at the problem of solving, uh, finding out the sorted order of three numbers. I'm representing in terms of a tree, right? And uh, no, it's not. You didn't get the point. So if I take some numbers, right? So what is the problem? So in your problem, it's not an execution of an algorithm. So it's a problem. What is a sorting problem? I'll give you some numbers. These numbers can be anything, A1, A2, A3, right? And I have to figure out which is the correct order of these three numbers, right? That is the problem. And in this way, I'm actually figuring out what is the process I should follow to get to a sorted order. Okay. If I take some fixed numbers like 759, okay, so then it will follow a particular path, right? It may follow this path. Okay. Total number of possible sets to n. Oh, we'll do all those analysis. But first of all, is this idea of decision tree okay with you? We are representing an algorithm in terms of a decision tree. Okay, so let me write it. Okay, what's a decision tree? It's a any comparison based algorithm can be viewed as a tree of all possible comparisons, whatever comparisons we are doing in the process, right? And their outcome, right? So so here's the thing. So I'm looking at their comparisons, right, and their outcomes. Okay, and also the resulting solution. Right. So what's the resulting solution in our case? These are the solutions. Right. So see, uh, in this decision tree, I have followed certain things like the comparisons. I am I am highlighting them as a oval shape, and the outcome of the comparisons are denoted by these directional arrows. Okay? And the final solution, the resulting solution, are given in a rectangular box. Okay, is it clear? And see what I have written here. I nowhere in here, nowhere I have mentioned that this is for sorting problem. No. So it's in general, I'm writing this in general. So for some problem, if you are to apply some comparison based algorithm, that algorithm you can view as uh, some nodes where you represent the comparisons and their outcomes, and there could be many possible comparisons and the resulting answers, right? Okay. Any question about this decision tree? What is it? This is, remember that this is representing some kind of an algorithm. Okay. So let me ask this. Let's say uh, some kind of comparison based, right? And let us try to draw some analogy between these two ideas. It's an algorithm, comparison-based algorithm, and its corresponding decision tree. So as I said, like we're looking at the same thing, a method of solving a particular problem. One is an algorithm, another one is a decision tree. Both of them are representing the same thing. Yes, everyone okay with this? Okay, fine. Now, just a second. Okay. Now let me ask you something. Right. So in these are comparison based algorithms. Uh, can you tell me one comparison in my comparison based algorithm? So whatever algorithm is this, there in this algorithm there must be some kind of a comparison, many comparisons. One particular comparison, if I see, what does that correspond to in a decision tree? What represents a comparison in a decision tree? Is this question clear? Question is, I'm saying that algorithms, comparison-based algorithms and decision trees are the same thing, representing a method of solution for a method of getting to a solution, right, for some problem. So now I'll try to figure out some analogies between these two things. My question is, in that comparison-based algorithm, at some point I'm using some kind of a comparison. What does that represent in a decision tree? Basically, I'm asking, what do you call these things? These are these are nodes. Any nodes? These are also some nodes, right? Can you give the precise answer? Leaf node? Comparison node? No, nothing. These are called internal nodes. I'm sure you have heard this, right? So there are two types of nodes in a tree. One is a leaf node, and other ones are the internal nodes. If a node is not a leaf node means its degree is one. It doesn't have anything below, right? Where the branch of the tree ends. right? That's called a leap. For example, these are the leap. This is one leap, right? And the all the other nodes from where you can still have some other, further down the line you can move. Those are called the internal nodes, right? So a comparison in an algorithm is corresponding to an internal node in the decision tree, right? Internal nodes in a decision tree is actually representing a comparison in this. Okay. Uh, what is the solution? What is the thing that represents a solution? Right. So solution is actually the leaf nodes, right? You got it right. Okay. Now, one more thing. This is an important thing. In the decision tree, let's say I'm asking a route or a path. I'll say a path from the root to a leaf node. Just think about there's no parent node. Is there no parent node? Uh, Parent of what? The root does not have any parent. Other than the root, everyone is having some parent, right? Yes. Now I'm asking, what is, think about a path from the root to a leaf node. It's something like this branch. It's a path from this to this. What does this represent in terms of an algorithm? Actually, I gave you the answer already. Let's say uh, just let me tell you, let's take some fixed numbers for the time. So three numbers if I take, a specific input if I give to this particular problem. So let's say, for example, I give you it's a 5 and 12, 9, right? So what does this tell you? So it's going to compare. This is my A1, A2, A3. Right? So first it's going to compare these two A1, A2, right? So is this true? A1, A2, if 5 is lesser equal to 12, it's yes. So it will come at this branch. Then we're going to compare A2, A3. 12 is less than 9 or not? The answer is no. So I'll come along this branch, right? And then I'm going to compare A1 and A3, and then I'll get this answer to be yes. So basically, I'm saying this path. What is this then? What do we call this? in terms of an algorithm? Iteration, getting loop. No. So this is but so this whole thing is an algorithm. Right? Decision tree is representing an algorithm. This whole thing is an algorithm. If I follow one particular path of it, right, then this is just an execution of that algorithm. One particular execution. If you give me this particular input 5, 12, and 9, then 12 बजे क्या? If you give me this particular input, then I'm going to follow this, right? So this particular branch is showing one particular execution of the algorithm. So not the depth. Depth is what's the length of that. So I'll come to that. Okay. So what should I write here? A path from the root to a leaf node, that is an execution of the algorithm. Is this clear? Right? So now let's come to length of such a path. What does that represent? Oh, it's not clear. So I'm saying when you give me a specific input, so I have to execute our algorithm on this input, right? So execution means first I compare these two, I'll come here. Then I compare A2, A3, then I go there. Then I compare A1, A3, I go there. This is one particular execution of this algorithm. That is what I said. A path from the root to the leaf node is actually representing an execution of that algorithm. Now, what do you call the length of that path? So length of that path, so this particular path is 3. This actually tells you the number of comparisons, number of internal nodes that you are facing. Not nodes, the number of internal nodes that you are facing. That is the length of the path, right? And internal nodes are basically the comparisons, right? So the length of the path can be is actually the number of comparisons, number of comparisons for that execution, for that execution. Okay, is this clear? Okay. Now comes the main question. What would be, so this is representing an algorithm, right? So, so this is also this number of comparisons. I can think this one as the running time of that execution, right? Now, can you tell me what does, so let me just put some demarcation there. Okay, so far so good. Now, can you tell me uh, what does this height of the decision tree? What do you call it? The height of the decision tree in terms of number of edges? No, there are many number like height. What is the height of this tree? By the way, what's the height of this particular tree? Height of this tree is 3. Right? Does this height represents the number of comparisons for what? Number of comparisons uh, in a particular execution is what we have seen is the length of one particular path. I'm asking what is the quantity that the height of this tree represent? Okay, so let me give you some hint. If I follow this execution, then if I follow this execution, then it will give me some number, some amount. What is the running time for that particular execution? If I take this one, it will give me for some other input, what is the running time? If I follow this, it's tell me for another input, what's the running time? If I go there, it will also tell me what's the running time for another input. So height is basically the length of the maximum such path from root to the lead. Like longest path you take, that's the height. And in terms of algorithm, what is that? What do you call that number in terms of the algorithm? In terms of the algorithm, depth, everyone knows like height, depth. In terms of algorithm, I am asking. That is what basically worst case running time. Right? This is the worst case running time. Why? Because it tells you like for some, this is the running time. For some other input, this is the running time. For some other input, this one is the running time. This, and this. This is the running time for some other input. Right? So maximum height. So height is basically saying what's the maximum length from the root to a leaf, right? And that actually represents what's the worst case running time for that algorithm. So these are the main thing to understand the relation between algorithm and the decision tree. Any question with this? Once you understand this, then from this we'll do something and then we'll get the result. Any question regarding these analogies? Okay, fine. Now, just think what we're trying to prove here. We're trying to prove something like this, that there does not exist any algorithm which runs better than this time, right? And we have just now seen that any comparison based algorithm I can view in terms of a tree, And the running time, worst case running time, is basically the height of the tree. Okay. Yes, that we have just argued. Right? So in terms of this decision tree, what do I have to tell now? To prove this result, we have to actually show that if I consider all the decision trees, if I consider all the decision trees that represent some comparison based sorting algorithm, then all the trees should be having height at least n log n. Is this clear? So let me restate what I just to show our lower bound, we have to prove that I'm again just restating the same thing, but this time this result is mentioned in terms of uh, comparison based sorting algorithm. Now we have this analogy between comparison and sorting algorithms and a decision tree, right? I'm writing the same result in terms of a decision tree. So to show our lower bound, we have to prove that every decision tree corresponding to corresponding to some comparison based sorting algorithm has height at least n log n. Is this clear? Right. So the algorithm, some result that says something about the algorithm, I'm representing the same result in terms of a decision tree. So basically, I have to show that among all possible decision trees that solve actually that represent some comparison based sorting algorithm, their height should be more than n log n. If I can show that then we're done. Okay. So basically, I'm going to prove this double stuff. Okay. Uh, Now, first thing is to understand what is the possible number of solutions. So, number of possible solutions of sorting problem. What is that? So I have, let's say, an input of size n. Okay, so not 6 in terms of n. So how many possible solutions could be there if I give you yes, it's n factorial. right? It's n factorial. Why? It's any permutation, any permutation of these n objects is a possible solution. Right? Everyone agrees with this? Okay. Now what? Um, Now, if my algorithm is correct, then it must contain uh, in the decision tree, I must be having all of this n factorial many possible solutions, and those solutions will appear at the leaf node. So for any correct algorithm, all of these factorial n many solutions must appear at the leaf node, must appear at the leaf node, must appear as a leaf node, so as a leaf node in the decision tree, right? Is this clear? So now I'll just try to figure out what would be the maximum number of leaf nodes possible. Okay. So from this, what I can argue from this, I can argue that so these are the number of possible solutions, and let's say let L be the number of leaves. Okay? So what is the relation between factorial n and this L? Number of leaves, what is the relation? Which one should be bigger? Which one should be smaller? Yes, L should be bigger, right? Because it could be equal also. Yes, it could be equal also. But so since L is the number of leaves and all the possible solutions, all the n factorial many possible solutions must appear as a leaf in the decision tree. Therefore, factorial n less or equal to L. Okay. Right. This is uh, y lesser. Oh, so you were thinking that, okay, it could be equal always. Right? Okay. So one thing is that it, you can appear at one particular solution uh, in many different ways. Right? For example, if in this one, in this particular, the way of representing this, the algorithm that we have uh, the algorithm for which we have drawn this decision tree, here we have got this only factorial 3 many leaves, but it might not be the case always. Why I am saying this? Maybe in your algorithm, you perform several unnecessary comparisons. Okay, so again, so that would lead to even further branching. Okay, and as your branching grows, the number of leaves will be more, but your number of possible solutions will remain as it is. It depends on the problem itself. Like once you give the problem statement, then the number of possible solution is fixed, right? But if you keep on doing some unnecessary comparisons, the branching will increase, and at the same time, the number of leaves will also increase. That's why I have written its L is greater equal to the possible number of solutions. Yes, okay, fine. Uh, right. Now let's try to figure out. So what is our goal? Our goal is to figure out what's the height of this tree. Okay, so has height at least this, right? So if let a decision tree of height h tree of height h can have what can I say? Like how many leaves can this decision tree have? Can have these many leaves. Can you fill the gap? So decision tree is kind of a hint is that decision tree is binary tree. It's kind of a binary tree. So you have two options, yes or no. What's the maximum number of leaves that's possible of a tree of height h? So just a single node, right? Just a single node. What's the height of this tree? Is zero. Okay? So this is a height one tree. This tree is having height one. Number of so okay, let me height zero is the number of leaves. Like this one, I can think on this firstly. Okay. So this is height one. How many leaves that this can have? This. Now think about maximum number of leaves that we are trying to figure out. For H2, how many leaves do you have? Right. So yes, you have already figured it out. The decision tree of height H can have, it's not always 2 to the power H, let's say at most 2 to the power H many leaves, right? So that basically says that L number of leaves is at most this, okay? Right? So what do I have here? So I have these two equations with me. Factorial n is lesser equal to L. and this L is indeed less or equal to 2 to the power h. So from the two above equations, we have, what do I have? Uh, Factorial n is less or equal to 2 to the power h. So what can I say about this h? H is greater equal to log of n factorial. Yes. Okay. Now what is this log of n factorial? So I can write this log of n factorial as omega of n log n. Why? Uh, it's because it's actually easy to see. So n factorial means what? N factorial means, okay, let me write it separately. So n factorial means like it's n times n minus 1 times n minus 2. This is n factorial, right? N factorial means this. All the way up to, let's say, n by 2 somewhere we'll have, and then n by 2 minus a 1. Okay? And, I'll write the before number of it. So n by 2 plus a 1, then n by 2, n by 2 minus a 1, all the way up to 1. Right? This is factorial n. Okay. So what if I replace, what if I remove this part? So this is n factorial is greater than n minus 1 all the way up to n by 2. Uh, okay, so how many terms are there? These many terms. Right? And again, I remove them. So n by, so how many terms are there? N by 2. Right? So what if I replace everything by, again, not equal, you can say strictly this. I replace everything by n by 2. Okay. So how many n by 2s are there? N by 2 many? N by 2 of them. So this I can write as something more than n by 2 to the power n by 2. Is this okay? So I can write this one as log n by 2 to the power n by 2. And this is nothing but n by 2 log n by 2. Okay? And h is greater equal to this quantity. So that says h is, this is in terms of omega notation, this is n log n. The constant doesn't matter. N log n. Is this okay? Any question regarding this? So what we have proved, like for any decision tree, uh, Last last one is this. So this factorial n is equal to this. This is the factorial formula. What I have done, this part I have thrown away. So this factorial n is bigger than this quantity up to this portion, right? And this is nothing but, so this is n minus 1, and the smallest of them is n by 2. I'm replacing all of these previous terms by n by 2, everyone. And how many terms do I have? In total, I have n terms. I have taken half of this. It's n by 2 many terms I have, right? So this is nothing but n by 2, n by 2 into n by 2, and this is n by 2 many terms. So it's like n by 2 to the power n by 2. So that is what I have used in here. N factorial, I have replaced this by n by 2 to the power s. This is n by 2 log n by 2. Okay. And why is this uh, omega of n log n? Calculation is not good. Uh, which calculation? This one, this, everything I have written here. So maybe you may not get this one. And for that, I'll suggest you to go back and check the definition of these notations. These are, I'm just playing with some inequalities. Some terms I'm throwing away and then I'm just replacing. So H is always has to be some constant multiple of n log n, right? So this is the lower bound for comparison based sorting algorithm. Okay, I hope you got this. So that completes the proof here. Next thing that we'll do is we'll try to figure out, we'll now restrict ourselves. Uh, Still, we'll see some variations of sorting problem. Right? So, what are those variations? Like this time, we'll assume that we are sorting numbers only. We're sorting uh, few numbers. So earlier, I said we were sorting some objects. Those objects are from some well-ordered set. Now, what we have seen, I can do it in n log n time, but in merge sort, using merge sort, I can do it in n log n time. But in practice, we use randomized quicksort, which gives on an average n log n time. Right? And today we have just seen that n log n is the best thing that we can do, because I just proved that less than n log n, it's not possible to have any comparison based sorting algorithms. Right? Now, what if I have as my input, instead of any general objects, what if I have some numbers with me, that those numbers I want to sort, and the tool that I'll be using for sorting those numbers are the numeric values of those numbers or some other properties of those numbers. using without getting into the comparisons, by using some other way, can I sort the numbers in better than n log n time? Uh, can we sort numbers in better than n log n? Means I want in linear time. Can I do this? Okay. The answer is yes, but it's not always. Yes, under certain cases. So what we're going to study now, or maybe in the next class mainly, uh, linear time sorting algorithms. Right? Okay, so one particular thing is kind of trivial. So suppose, assume that we are given n numbers, and all of those numbers are from 0 to 9. Okay, is this assumption clear? So I'm not saying I'm given only 10 numbers or 5 numbers, 10, 6 numbers or 10, 20 numbers. You can give me any number of integers, but here's the assumption. All the numbers are either a 0 or a 1 or a 2 or a 9, like this. The range of the values that these n numbers can be. So if I rewrite this, this is my input as before. And what's the assumption? Assumption is AIs, all of these AIs are from this set. Now, in this setting, can I sort this number? I think it's very intuitive also. How can you sort these n numbers? If I tell you that these numbers are from just can take 10 different values. Yes, anyone would like to suggest? So one thing I can do is I'll maintain some arrays of numbers. Let's say this is the 0, this is for 1, this is for 2, and I'll go down the line, and the last one is for 9. Right? If I see a 0, then I'll append it here. It's basically I'm trying to figure out some kind of a list. If I see a 2, then I'll put it in the list of this 2 there. Right. So like this, I'll store all these numbers. Okay. So I'll store them in this way. And then how do I print? So while printing, I just scan through this array of numbers, and if this one is a 5, I'll put it a1 in the list of 5. Like if this is 0, then I'll put it here. If this one is 9, I'll put it here. If this one is 7, I'll put it in this list, like this. For every number, I'll do this. Okay. And then what I do once I store all these numbers in this way, then I print first this whole list, then I'll print this whole list, then I'll print this next list. At the very end, I'll print this list. Right? In this way, I'll be able to sort it. You got this idea? Now, how much time does this take? Okay, by the way, let me ask you, do you know these lists, linked list? Yes, okay. Right. So these are the linked lists that we are using here. Right? Okay. How much time does this take? You know also stacks and queues also. Do you know what's a queue? What's a stack? Right? Okay. Okay. So think these things as queues. Yes, LIFO, FIFO, and all of this. How much time would you take to uh, put all these numbers into one of these lists? Here, see, I will just check the numeric value of these numbers, and I can straight away go to that particular queue and insert there. I can insert at the very end of this list, right? In constant time. Okay? So overall, creating this type of structure would cost me O of n time, right? And while printing, I have to just print these queues also. In total, what's the size of this? Uh, in total, how many nodes do I have in here? N nodes. And also, each of them comes with uh, of this end of this list character, right? And therefore, it's going to take this n plus this number of different values that we can have. Why size of the linked list is different? Yes. Why the size? Do you think all these linked lists will have equal size? No, right? It really depends on how many. So, what would be the size of zero? What would be the size of this linked list? It will be the number of zeros that we have. That is frequency of zero in this input. So, suppose I have only one zero. Out of all these n numbers, I have only one zero. So, the size of this list will be one. Or rather, I have 55 many nines. Then this list will be, the list corresponding to 9 will be of length 55, right? So these linked lists will be of different sizes. Okay. Okay. So Having said that, we can see that the time taken for this one would be O of n plus something, some k, I'd say, where this k is the number of different values that AIs can take. So AIs are taking can take nine different values. In this case, k is nine. But in general, so I'll write this algorithm again since we don't have much time left or almost finished the time. So we'll again continue with this particular algorithm for sorting n numbers under certain assumption, right? So we'll see few other linear sorting algorithms for sorting integers or numbers in general. Okay. But do you have any question regarding this particular process, that particular algorithm? Okay. Okay, fine. So I'll tell you what this K is all about. I'll write the input as well, input to this problem. Okay, that calculation. Yes, any question? Okay, okay, fine. So now then let me close this meeting now. Okay, thank you.